Hi, this is Ben Goodrich, and this is the replacement video for Section 7, which was actually yesterday, but I accidentally was screencasting the wrong window, and so only the audio got captured rather than the screencast. So we'll just do it again now. There's a file on Courseworks under Section Material. It's a large zip file that you can download, and we'll have the RMD file that I'm working from here, a variety of .stan files that we'll go over the next hour, and a bunch of .rdata files which obtain or contain the output of various STAN models that I've already run and saved the results of because they take, in some cases, a few minutes or even longer to run. And so it's a bit tedious to run them yourself. Instead, this .rmd file will have those in eval equal false knitter chunks, and it'll just load the already saved object, and we'll make plots and do diagnostics and stuff from there. So two packages that we're going to need today are the energy package and the Lars package. And we're going to start off with an example of comparing a probit model, the same probit model, across four Markov chain Monte Carlo algorithms. So we're going to sample from a posterior distribution that is based on a probit log likelihood, which we can write as an R function as follows. It's going to take some unknown parameters beta, a predictor matrix X, some binary outcomes Y, and the log likelihood is just the sum of the Bernoulli distribution, which is a special case of the binomial distribution with size equal to 1. So we're going to evaluate that Bernoulli distribution at the sample values of Y, with the probability equal to x times beta, which generates the linear predictor, and then that is mapped to the 0, 1 interval using the standard normal CDF in this case. That's what makes this a probit model. If it were a logit model, we would use the standard logistic CDF, p-logis. This ought to make it clear that any CDF from the real whose sample space is based on the real numbers would be a candidate transformation for this linear predictor to the space of probabilities. But to keep things simple and to facilitate comparisons across algorithms, we're going to use the standard normal CDF and thus deem this a probit model. We take these Bernoulli probability mass functions in log form and sum them over the entire sample to get a log likelihood for a sample evaluated at some proposal for beta. Now, not that we would recommend that you would do this in actual work, but we're going to we're going to have improper priors on the coefficients, so the posterior distribution is just proportional to the log likelihood. That's going to work decently well in this particular situation, where we have an example on predicting the incidence of low birth weight births. This data set comes from the MCMC pack R package, and it has 100 something observations. So there's no great concern about using improper priors on the betas in a model as simple as this when we have adequate data. So we're going to also show how you can use the model frame function. If you pass that a formula and a data set, it will prepare that for estimation in models. This is useful because it will convert factors into a sequence of dummy variables. It will limit the data set to complete cases on the variables in the model, etc. So it's pretty convenient. Given that model frame, we can extract the response and call that y. It's based on the variable low in the data set birth weight, which is 1 if the baby is born with low birth weight and 0 otherwise. We can also use the model matrix function, which takes similar arguments in order to construct the X matrix that corresponds to this particular formula. So a couple of weeks ago, I showed an example of using the R-Uniron package to do Gibbs sampling. And at the time, I said that you shouldn't actually use that function, but it was a nice thing to study in order to understand not only Gibbs sampling, but also the approach taken by the R-Uniron package to be sort of a universal way to draw from univariate distributions. And so it's going to cycle over the iterations. It's going to cycle over the variables. It's going to create a full conditional distribution for the kth element of theta, conditional on all the other elements of theta. And given that full conditional function, we can pass it inside the loop to the PIMV new function in the R-Uniron package, which will generate an approximate inverse CDF for that kernel based on polynomials. We'll then pass that to the UR function in the R-Uniron package to get one draw from this full conditional distribution and put it into the kth element of theta, whereupon the next element of theta will condition on the draw that we just obtained, etc. And going through all the variables and over a bunch of iterations, we can obtain draws from essentially any posterior distribution where the variables in the posterior are all continuous. But like I said, we shouldn't actually use that function because its performance turns out to be not very good, and it's also extremely slow. So it's extremely slow even if we start the chain at the maximum likelihood estimate. So you can use the GLM function with family equal binomial link equal probit to obtain maximum likelihood estimates of the probit model, which is sort of a convenient starting point for a Markov chain. And so, like I said, this actually takes about 2 hours to run. So you don't want to actually run this line. It's in the other .rmd file. It's enclosed in a block with a value equal false. In any event, yesterday I ran this pretty much all morning and was able to obtain 8 chains, a few thousand iterations based on this Gibbs sampler, and to save it to the disk, whereupon it can be loaded into the R session and we can manipulate it a bit. So I'll flip now to the RMD file, run all this, and load in the r/unron.rdata file from my working directory. So we can compare that to a Metropolis Hastings approach to the probit model. So the MCMC pack has an MCMC probit function, and we're going to see that shortly, which is customized for probit models. But MCMC pack also has a fairly universal Metropolis Hastings sampler based on multivariate normal random walk proposals that we can use in order to compare Metropolis Hastings to other approaches to estimating a probit model. And so the MCMC Metrop 1R takes the following arguments. The function that you want to be the posterior that you draw from, initial values of theta, various other arguments. I'll choose tune to be a little bit bigger than the default in order to get a acceptance rate of near the optimal number of about 0.234. I also, whenever you're calling functions in MCMC pack by default. If you're doing multiple chains, it will use the same seed every time, in which case you'll get the same draws for all of your chains, which is not what you want. So in order to give it a different seed for each of these 8 chains that I'm going to run, I'm going to sample an integer for all the integers that R knows about and use that as my seed each time. Also going to pass it X and Y, which are functions or objects that in turn get passed to the probit log likelihood function that I defined before. So this actually runs pretty quickly. I don't think I have the parallel library loaded. So this should have and at that point, it should be ready to go here, although for some reason it's throwing me an error message saying I didn't paste in my likelihood function. So go back up here, type in that chunk. So the MCLApply function won't, well, I think it does technically work on Windows, but it won't go in parallel on Windows. But this is probably fast enough that it doesn't really matter. So just in the time that it took me to explain why it was going to not work on Windows as well, it's already done on my computer. So I will then just do this thing, which will put the names of the variables onto the parameters, and then we'd be ready to inspect this object. So if we wanted to, we could look at the output from that Metropolis Hastings sampler. We get means and posterior means, posterior standard deviations for each of the predictors we put in the model, age, 2 race categories, and a binary variable indicating whether the mother smoked during pregnancy. We also see the median and the other quantiles of these draws from the posterior distribution obtained with a Metropolis Hastings random walk sampler with multivariate normal proposals. So now we can compare that to the approach in STAN. So in order to do STAN, you have to write your own .stan program, but that's not too difficult to do. So here I've written one for a probit model. We're going to declare an integer n for the sample size, an integer k for the number of predictors. Given those two things, we can then declare an n by k matrix X of predictors. And for the outcome, remember that STAN, ordinarily you might be tempted to declare this as a vector of length n, but STAN considers vectors to contain real numbers. So if you want to pass in a discrete outcome, you need to declare it as an array of length n of integers, in this case, integers between 0 and 1. I should have said before, if I haven't said already, that these lower and upper bounds in STAN are interpreted inclusively. So for binary data that are either 0 or 1, they're going to satisfy these constraints here. So the only unknown parameters in a probit model are the vector of coefficients. This is a vector of length k, which we'll call beta. And then all the action happens inside the model block. To make this as easy as possible, I declared 2 local vectors, eta and p. So those have to be declared at the top of the model block, but they are not going to be stored. They're not really interesting enough to keep samples on, and if I really wanted to, I could obtain them in R fairly easily. So eta is just going to be the linear predictor, the product of the matrix X and the vector beta, and then to fill in the p vector, I'm just going to loop over all n of the observations, and in each element of p, I'm going to pass the corresponding element of eta to the phi function, recall the phi is a typical notation to indicate the standard normal CDF. So that's going to take this real number and map it using the standard normal CDF to the 0, 1 interval so we can interpret it as a probability. And we'll do that for all the observations in the sample. So then I just pass the P vector, which I just created, to the Bernoulli sampling statement. So this says that my likelihood is a sum of conditionally independent Bernoulli observations that have the corresponding element of P as the probability of having a child that's low birth weight. Now, remember, a lot of people, when they're first learning STAN, would be tempted to do something like this, where they put the likelihood statement inside a loop. Now, as we said briefly last week, but it bears repeating, that this is equivalent but a much slower way in STAN. The reason why that's true is anytime you have a tilde sampling statement or you call increment log prob, manually, STAN has to go through and allocate memory in order to hold the partial derivatives of everything and to put everything in the right place in memory, so then it can sweep over all that to take into account the chain rule. And really, the slowest part of STAN is the sort of putting all these partial derivatives into the proper places so it can evaluate the chain rule. And if you put your likelihood inside a loop over all the observations, STAN doesn't know that in the next iteration of the loop, you're going to be basically doing exactly the same thing, just with a different observation. And consequently, it has to allocate memory for holding all these derivatives n times. Whereas if you do this the correct way, or at least the faster way, then this takes the whole sample of observations at once and a corresponding vector of the same length of probabilities. And STAN can utilize the fact that when it's getting the log likelihood for the entire sample, that the derivative of a sum is equal to the sum of the derivatives with respect to whatever parameter we're talking about, some element of beta. And so inside the Bernoulli function, if you pass it the entire sample on the outcome variable, it only has to allocate memory to hold those partial derivatives once. And then inside the Bernoulli function, it loops over the sample and it accumulates up the log likelihood, and it also accumulates up the derivatives in the space on the computer's memory where it's allocated that. And so that is really one of the best ways to get faster speed from STAN, is to utilize sampling statements, particularly for the likelihood, where you pass as much of the likelihood to it as you can in one batch, and that makes STAN run a lot faster in terms of wall time, and it's not changing what you specify for your model at all, assuming the observations are conditionally independent. So that's the probit.stan function that we're going to call with the STAN function. Again, in order to use STAN, you have to pass it a list of data that is a named list that has all of the same elements that are declared in the data block of your STAN program. So this will take a second to compile, actually probably more like 20 seconds. But and in a lot of situations, this is the slowest part of calling STAN. It'll run pretty quickly once it's translated this to C++ and compiled, which it's done now. It's going to run 8 chains, which is more than the default of 4 in STAN. But as I mentioned in class this week, I think the default of 4 is a little bit too small to do the diagnostics that we want to encourage in this class, even though it probably gets more draws from the posterior distribution than we really need. We need that many draws in order to do an adequate diagnosis of whether these draws seem to be legitimate, to verify that nothing has gone wrong with the calculations, etc. So we'll get to that a little bit more next week, and also later on in this video segment. But for now, we just want to move on and compare the three variations on the probit model, sampling from a probit model, or sampling from the posterior distribution of a probit model, to arguably the best one, which is to use the MCMC probit function in the MCMC pack R package. And if we remember back a couple weeks ago, we said that for a binary probit model, it's possible to introduce a latent utility for every observation. And when you do that, the full conditional distribution of the coefficients depends on the latent utility, but it does not depend on the observed values of y. And the full conditional distribution of the latent utility for each observation is simply going to be a truncated univariate normal, either truncated from below at 0 if y is observed to be 1, or truncated from above at 0 if y is observed to be 0. And so if it can draw those latent utilities from a truncated univariate normal and then condition on those latent utilities in order to draw the whole vector of coefficients from a multivariate normal, then the MCMC probit approach using these latent utility, which is also called data augmentation, can not only execute really fast, it also gets draws that have fairly minimal dependence in MCMC time, because this approach in this particular case overcomes the sort of fundamental limitation of Gibbs samplers, where if it can't draw all the parameters at once, it gets into a situation where the full conditional variance of some parameter is much smaller than its marginal variance, and thus the draws from the full conditional distribution don't there's only make small steps away from wherever the chain is currently, and that can lead to Gibbs samplers that take a long time to reach the posterior distribution, that mix slowly, that have high variance inflation factors due to the infinite sum of the autocorrelations, consequently have lower effective sample size for a given nominal size, etc. So that is really, and we'll see this more in a minute, what happens and adversely affects the Gibbs sampler that we wrote to use the R Uneron package, because it updates one parameter at a time. The full conditional distribution of each of those parameters has each of those, the variance of those full conditional distributions for each of those parameters is smaller than the marginal variance, and thus it makes relatively small steps compared to the Gibbs sampler that introduces latent utility as a augmented data, and thus gets a form where it can update all the coefficients at once. And even if those coefficients are correlated, so it's drawing from a multivariate normal distribution with a dense covariance matrix, that's still fine. It gets draws that are relatively far from the current draw, and is still accepting those with probability 1. So this also runs extremely quickly. Oops, unless I made a mistake. Also runs extremely quickly, and this will allow us to compare these four approaches. So to do that, you want to source in the dependence.r function that I believe I included in the zip file on CourseWorks. Just make sure that you've changed the working directory to the place where you unzipped the zip file for today, and it will be able to find all the files that it needs directly underneath that directory. So we're going to compare these four approaches. This just sets up the margins and whatnot for the plots that I want to show. And I'm going to call the dependence function on each of these four sets of draws from the posterior distribution, the same posterior distribution. And this is going to produce the function that I was showing in lecture on Thursday. So it's not going to look great like this. Let me blow it up and call those again. Okay, and if I zoom and if I pop, this is not working. Oh, you can see it here. So, well, it's decent. In any event, the one in the top left is the draws from based on the draws from the R Uneron approach, and actually you can see it probably better here. So all these different colors correspond to a different number of lag lengths. We have each of the 2,000 iterations here along the horizontal axis, and on the vertical axis each time we have the estimated distance correlation between, you know, a draw, let's say here at 1300 and 1301 if the lag length is 1, or 1303 if the lag length is 3, 1313 if the lag length is 13, etc. And we can calculate those over all 2,000 draws that we obtained from the posterior distribution. So as you can see from this plot, even after 13 lags, it's not the case that the draw now is essentially independent of where it was 13 iterations ago or where it was going to be 13 iterations in the future, because independence is characterized by distance correlation, at least the distance correlation in the population as being 0. That characterizes independence between vector valued random variables. And what we would like to see is for some lag length, the distance correlation gets to be essentially 0 and stays 0 throughout the entire post burn-in period, which doesn't occur in this case. It looks like it might get down close to 0 for 12, 13 lags right at the end of our sampling period, but we would prefer that it get close to 0 and stay close to 0 for it, you know, at least half of this. And, you know, we could throw away the first half and analyze the second maybe. So without, and, you know, I could have done it at bigger lag lengths and maybe seen something closer to 0, etc. But if you can't find a lag length such that the estimated distance correlation gets near 0 and stays near 0 for the entire post burn-in period, then you can't really do the test that we talked about on Thursday, and we'll see an example of next, to test the null hypothesis that all the chains have the same distribution, because there is still dependence within each chain that's going to violate the assumption of the permutation test that the draws are independent within chains. So this is an example of the R-Uneron approach to Gibbs sampling not yielding great performance even on a relatively simple probit model. In the top right, we have the same basic thing, but it comes from the Metropolis-Hastings approach to estimating a probit model. And so here we see that after 12, 13 lags, the distance correlation seems to get essentially zero and stay more or less close to zero, except maybe the last 100 iterations or so, it kind of looks like it bounces off zero again. Sometimes that can be an artifact of the fact the way this plot is drawn. It does smoothing to create these lines, and that can create edge effects because there is no 2001 iteration, etc. And so sometimes these sort of take off things at the end of the sampling period can be kind of a red herring. But in any event, as a matter of comparison, clearly the Metropolis-Hastings sampler, which can take an arbitrary R function to define the kernel of the posterior distribution, is performing better than the R-Uneron approach that's based on the same posterior kernel, because at least this gets close to independence after 12 or 13 lags of the Markov chain, whereas the R-Uneron one didn't, except maybe toward the very end. Moreover, if you remember, the Metropolis-Hastings one took probably about a second, and the R-Uneron approach took me most of Friday morning to run. So clearly, the performance on this criterion of the random walk Metropolis Hastings sampler is better than the R-Uneron approach to Gibbs sampling, even though they're both universal in the sense they can take any posterior distribution that you can throw at it, and in principle it will draw from that posterior distribution. It's just, in this case, and it's something that you would find in general, the Metropolis-Hastings approach is more efficient than the R-Uneron approach. In the bottom left, we have the probit model, again based on the same log likelihood that is estimated using the Nuts algorithm in Stan. And here we see some things that are pretty typical. First, for one lag, it's often the case that the dependence decreases for the first 100 iterations or so. That's because the chains, the 8 chains that we're using to calculate these distance correlations, are starting off not in the posterior distribution. They're starting off in different places, and thus they have more within chain dependence, less within chain distance relative to between chain distance at the initial period than they do later on. So after 100 iterations or so, the between chain distance between the 8 chains is decreasing, and thus the ratio of B to W you would expect to be smaller, etc. So this is pretty typical of something that we see in Stan. After that, the dependence stays relatively constant for one lag. By construction of a Markov chain, the draws in the next period are going to depend on the draw this period, but conditional on the draw this period doesn't depend on the draw any time in the past. So there's always going to be dependence, non-zero dependence for one lag. But you see in the case here that even 2, 3, 4 lags, the dependence is essentially zero and essentially stays zero throughout the entire post warm-up period for this model, which is really about as good performance as you could expect from a Markov chain. This also runs really fast in order once you get the thing compiled, and you only have to compile it once. And so on that criterion, we can say that the Stan approach, which is a special case of a Metropolis Hastings sampler, just using Hamiltonian dynamics in order to make proposals, and then using the Metropolis Hastings acceptance criterion to decide whether to accept those proposals, is more efficient and preferable to random walk Metropolis Hastings sampler, such as made available by MCMC Pack, which is basically just guessing proposals without using the gradients of the posterior distribution or any of the complicated physics that goes along with Hamiltonians, etc. And thus, it's pretty much generating proposals. It has an optimal acceptance rate of 0.234. So 3 out of your 4 draws, you're staying in the same place. And, that certainly doesn't seem very efficient, etc. Whereas Stan, by default, the acceptance probability, the targeted acceptance probability is 0.8. So we're obtaining proposals that we can accept with high probability, but due to the nuts mechanism, if it gets to the U-turn point and then stops to come up with its proposal, the proposals are going to tend to be not too close to where the chain is at time t, and thus you're able to get proposals that have not so much dependence on the current state, but are still accepted with high probability. And that's why the dependence among nearby draws basically dissipates after one lag. If we compare that to the results from MCMC Probit, which uses a Gibbs sampler and augments that with this latent utility variable, we can see it has about the same performance as Stan. The MCMC Probit function doesn't save the burn-in period, so this is actually the first draw after the burn-in period ended. It would be comparable to the first draw after warm-up ended in Stan. And so this is basically comparable to the second half of the Stan output. And you can see the Gibbs sampler also has, a distance correlation estimated maybe a little bit below 0.2 for its post-burn-in period. And after one lag, the dependence is essentially negligible for 2, 3, 4 lags in the future and the past, and it stays near 0 throughout the entire post-burn-in period. So in this respect, MCMC Probit is getting the sort of same low dependence in the draws. It also executes perhaps a little bit faster. So on that respect, you could say if you wanted to estimate a plain Probit model, then the MCMC Probit function in the MCMC-R package would certainly be a good choice for doing so. But the MCMC Probit function is tailored to a particular case and doesn't give you very much flexibility as to what you can do with it. So you would be allowed to choose any prior for the coefficients in the multivariate normal family, but if you wanted to use some prior on the coefficients that was not multivariate normal, then you would have a perfectly valid posterior distribution. It would just be a posterior distribution that could not be sampled from using Gibbs sampling, and you would have to fall back to Metropolis Hastings or something like that. Similarly, if you wanted to estimate a logit, estimate a draw from a posterior distribution based on a logit likelihood instead of a probit likelihood, there's not a whole lot of differences between those two models, but the logit likelihood function does not lend itself to Gibbs sampling. So again, we'd have to fall back on Metropolis Hastings, and so forth. So there's not really a whole lot you can do to change the model without making it difficult or impossible to use a Gibbs sampler for that model. And this particular Gibbs sampler achieves essentially the best case scenario for a Gibbs sampler because it can update all the coefficients from their multivariate normal full conditional distribution at once. It works well even if those coefficients have high correlations in the posterior distribution, etc. In any event, it can be proven that the Gibbs sampler, based on after introducing the latent utility variables, converges to the posterior distribution at a geometric rate, which is about as best you can do in non-trivial problems with continuous posterior or continuous parameters that you want the posterior distribution of. And so in that respect, the performance of Stan in this model is also very optimistic because it essentially achieves the same performance as the best case for a Gibbs sampler, yet Stan offers as much flexibility as Metropolis Hastings or this Gibbs sampling via the R-Uniron approach would. If we wanted to change this to a logit likelihood, we could. If we wanted to change the prior to be some other thing besides multivariate normal, we could, and it would just involve a couple lines change to our .stan program, and we would hope that we would be able to achieve about the same performance in that modified model as we do in this particular case, because there's nothing about the probit likelihood or the absence of proper priors that we chose in this case that's driving these results. If in the Stan case, it's not using conjugacy or any special tricks like that. It's just doing the nuts algorithm based on Hamiltonian dynamics. And in this case, albeit a relatively simple model, we get as good performance as in the best case for a Gibbs sampler. Now, in more complicated models, it might not look this good, but hopefully it will be the case that the dependence among draws gets to be zero and stays zero for the whole post warm-up period, within maybe 5 lags, perhaps 10 lags. If it's more than that, that usually suggests that your model is very complicated, or Stan might have difficulty sampling from that posterior distribution. So maybe you could go back and do some reparameterizations, double check to make sure you haven't made any mistakes, etc. But for well-written .stan programs, it will often be the case that you can see the dependence among draws dissipate within some single-digit number of lags, and then you can use that lag length as a thinning interval for the test that I'm going to show now of the null hypothesis that the chains have reached all the same distributions. So if we go back to the R code, so once you've identified a lag length that looks good, you want to look more closely at those, which we'll do for Stan on the top and MCMC probit on the bottom. These are both based on a lag length of 4. And when you do a particular lag length, the plots will show the dots, which are the estimated distance correlation at that time relative to the draw 4 lags away. The red line here is again the sort of smooth estimate. It looks like it's staying pretty close to 0 throughout the whole post warm-up period. That's good. Moreover, in this case, we can put a 95% confidence interval on this estimated distance correlation, assuming The number of parameters is large, which it isn't so much in this case, but it very well could be. And it seems as if probably less than 5% of these dots are getting outside the 95% confidence interval. So there's nothing in this plot to suggest that a thin interval of 4 would be inadequate. And a similar thing for the Gibbs sampler done by MCMC Probit. You see the occasional dot outside the 95% confidence interval, but that's probably less than 5% of the total dots. So that's not inconsistent with the conclusion that the draws are essentially independent of each other after when they're 4 lags apart. So in order to do the test of the null hypothesis that the chains all have the same distribution, I'm going to source in the convergence.r function and call the convergence test on the object that I obtained from the stand function. I'm going to pass it a thin interval of 4, which is to say I think that within each chain, the draws are essentially independent of where they are for lags into the past or into the future. And I want to do 199 permutations in order to get the null distribution for this test. So this runs relatively quickly if you have a pretty high capacity computer, and you can see the output of it, which is very similar to the ANOVA output. So the first thing to look at is the ratio of B to W, the between group distance to the within group distance on the thin chains. As I talked about on Thursday, this test actually does what amounts to a two-way ANOVA decomposition. So there's first going to be a contribution to the total energy distance at the chain level. There's also a contribution at what I call the split level. So that takes all 8 chains and pools together the first 500 draws in this case, and then all 8 chains pooling together the second 500. Well, they'll be thinned draws, so 500 over 4 draws from the second half of the chain. And so there's a contribution to the total energy distance that comes from, the first half of the draws and the second half of the draws. So even if the chains are not in the stationary distribution, but they're all still evolving at kind of the same rate toward the posterior distribution, then we'll see an outsized contribution to the between group distance when we split the draws this way that we might not see when we split the draws by chain over the entire post-warm-up period. And then again, consistent with this two-way ANOVA idea, there's the interaction between chain and split, which is basically to take all 8 thinned chains and to divide them into half chains and see what is the contribution to the total energy distance that comes from grouping at the half chain level. In any event, for each of those groups, we can calculate a ratio of the expected distance between group to the expected distance within group after thinning. And if we've thinned appropriately, then we would expect this ratio to be 1, which is to say the between group distance ought to be about the same as the within group distance. And we can see for each of these 3 factors, that is in fact the case. Now, sometimes the ratio will be a little bit over 1, and then you can turn to the p-value to see if these realizations of the B to W ratio are large relative to the distribution that was obtained under 199 permutations of the chain time structure. So in this case, we see all these p-values are much greater than 0.05 or 0.01, whatever threshold you want to use. And so we would fail to reject the null hypothesis that all the chains have the same distribution. And we could go on to analyze the results. We can do the same thing with the Gibbs sampler done by MCMC Probit. This is taking a little longer for some reason, but again, we get p-values that are far from the conventional cutoff levels, and so we would fail to reject the null hypothesis that the Gibbs sampler has produced chains that all have the same distribution. So at this point, we could go on to look at other diagnostics, or go on to make substantive conclusions about our results. In doing so, we do want to also look at the effective sample size for any of the parameters or functions of the parameters that may be of interest. In this case, we would probably be most concerned with the coefficient on the variable that's a binary variable for whether the mother smoked during pregnancy. So that has an average coefficient of 0.69, posterior standard deviation of 0.22, and so that's small relative to the mean. The 95% interval ranges from 0.25 to 1.13, doesn't include 0, and so on and so forth. Of course, in a probit model, you can really only look at the signs of the coefficients, which is to say, our posterior implies that we believe if the mother smokes, the probability is higher that she will have a low birth weight baby. But in order to actually say something concrete about that probability in a nonlinear model, we would have to draw from the posterior predictive distribution, comparing at some value of the x variables where the smoking variable is set to 1, and then compare that to the same set of x variables but changing the smoking variable to 0. Then we can see how the probability of obtaining a low birth weight birth changes for a given set of x variables in terms of age and race and all that. But those probabilities, because it's a nonlinear model, are going to depend on what x you use to draw from the posterior distribution, etc. So you can't say as much about the effect of smoking just from looking at the posterior distribution on the coefficient, except to say that we have essentially 0 posterior probability that smoking is not harmful for the baby. For any function of interest, we want to look at the effective sample size, which takes into account the dependence of the draws. In this case, there isn't that much dependence among the draws, and consequently the effective sample sizes are in the thousands, which is certainly more than enough to make inferences, precise inferences about the mean of some function. That's also reflected by this SE underscore mean, which is the Markov chain Monte Carlo standard error, which is essentially 0 to 2 decimal places for all of these, but might be somewhat larger if we were interested in some nonlinear function of the coefficients. So even after you've satisfied yourself that the chains have the same distribution, you want to look at the effective sample size to see if you're getting enough precision on the expectation of the function that is of interest to you. And again, recall that if you believe the draws are essentially independent after 4 lags, then that provides a lower bound for the effective sample size on any function. So in this case, we would have 8,000 draws. If we were to thin them every 4th, that would provide a lower bound of for the effective sample size of 2,000. And we can see in each of these cases, the estimated effective sample size is lower than 2,000. And so the method from this way is only a loose lower bound to the effective sample size. But if you see the estimated effective sample size being less than the lower bound implied by this exercise, that may imply that the Markov chain Monte Carlo central limit theorem, whether it holds, is a bit suspect in that particular case. Moving on, so that was a comparison of different NCMC algorithms on the same posterior distribution. Now we want to compare the same MCMC algorithm, namely the no U-turn sampler in STAN, to or under different parameterizations of the same prior. So I'm going to flip over to my PDF here and talk about the horseshoe prior. So the horseshoe prior is something that has become popular in certain circles as a prior for regression coefficients. It states that the regression coefficient is conditionally, or this should just be lambda, but in any event, it's normal with mean 0 and standard deviation lambda. So in this formulation, there shouldn't be a tau here. But lambda is something that varies from coefficient to coefficient, and lambda is distributed half Cauchy, which is to say the absolute value of a Cauchy random variable with median 0 and scale tau. Recall that for the Cauchy distribution, the scale is equal to half the interquartile range, but that's for a Cauchy distribution over the entire real line. Here, because the standard deviation has to be positive, we're interested in the absolute value of a Cauchy random variable, which basically doubles the density in the positive part of the real line. And in turn, tau, the scale parameter in the Cauchy distribution for lambda, also has a Cauchy distribution with median 0 and scale 1 over the positive part of the real line, so the absolute value of a Cauchy distribution. So we could easily simulate from the marginal distribution of beta by first drawing tau from a Cauchy distribution with median 0 and scale 1, then drawing lambda from and taking the absolute value, and then drawing from a Cauchy distribution with median 0, scale tau, take the absolute value of that to form draws of lambda, and then make draws of beta from normal distribution with location 0 and standard deviation lambda. So by construction, it is the case that tau and beta are uncorrelated with each other because tau only affects beta through the standard deviation. Although the estimate of it can be very noisy empirically because the distribution of tau has such a long positive tail. But also by construction, tau and beta are not independent of each other because tau is the scale parameter for lambda, and lambda is explicitly the standard deviation for beta. So if we load up the energy package, we can use the independence test in that package, which was mentioned in the reading this week on energy statistics, and we would see we would reject the null hypothesis that tau and beta are independent of each other. Or perhaps more directly, we can calculate the distance correlation, estimated distance correlation between tau and beta, and see that that is about 0.4, estimated to be about 0.4. And that is far from 0, where 0 would characterize independence between two variables. We can also make a plot of the marginal distribution of beta and compare that to other distributions. So I've done that here. You can see the horseshoe prior has a big spike at 0. And that reflects basically the prior hope that most of the coefficients in this regression model have a slope or the slope coefficients are going to be mostly near zero a priori. And so this horseshoe prior is often used in genetics and similar fields where they have a lot of predictors. In the case of genetics, you have as many predictors as there are chromosomes, which is some really big number. But for any particular hereditary disease that you might be investigating, you sort of hope that most of the chromosomes are irrelevant to this particular hereditary disease that you're studying, but there might be, you know, 1 in 100,000 chromosomes or something like that that actually has a big coefficient with respect to whatever symptoms you're measuring. And thus, the horseshoe prior puts a small but non-zero probability on very big coefficients, even, you know, bigger than what's seen here, where they go out to like negative 500 or 500, et cetera. So it's a prior distribution that is very concentrated on zero, but simultaneously has very, very long tails in order to allow a small possibility that some of the coefficients in the regression model actually do have really big effects. And then, you know, once you've narrowed down the set of chromosomes that you need to study in more detail, you might, you know, go try to find people who only differ on one chromosome or, you know, something like that in order to study the phenomenon more closely. I've also put a standard normal distribution for contrast, but you can't even really see it that well because it's, you know, like less than the pixels when the horseshoe prior is plotted. But you know what a standard normal one looks like, and so it has a much skinnier distribution and a much shorter peak. And so that's kind of what the horseshoe prior is all about. And then if we want to apply this, there's a data set for some symptom of diabetes. It's a continuous outcome. I'm not exactly sure what it is. There's a bunch of predictors that we'll make a matrix X out of. There's really, I think, only 10 predictors, but it also includes all the interactions among those 10 predictors. So that would be like 10 choose 2 more columns of X anyway. So it allows some nonlinearity in the relationship between the predictors and the outcome. We're going to round up N and K in order to form a list to pass to the stand program that corresponds to. So if we bring up that file, we can see that this starts off like a typical stand model for a regression. We have the number of observations, the number of predictors. That should probably also really be a lower bound of 1. Given those, we can create an n by k X matrix, and we have a vector of continuous outcomes. So as far as parameters, we're going to have an intercept that are basically just going to put an improper prior on. We have beta. For each beta, we have a lambda. We have tau governing the scale of all those lambdas, and we have sigma, the error variance for the regression. And so we'll just declare this the same as we saw in the PDF. Tau has a half Cauchy distribution with location 0 and scale 1. So this might seem a little weird to you since tau is declared with a lower bound of 0, but we're using a Cauchy distribution whose sample space is the entire real line. So in general, you want your prior distributions to have the same sample space as the support that you declared on the parameters in the parameters block. And failing that, you could use a truncated distribution, which is indicated in stand by the T and then brackets, and you can either put a lower truncation point or an upper truncation point or both. So this would not be wrong. However, if we look at this more carefully, we see the amount of prior mass that is truncated away is a constant, namely 0.5. So no matter what value tau takes, exactly half of the mass is truncated away. In which case, if we do the correction for truncation, we would be dividing the density by 1 minus 0.5, which is the amount of untruncated area. And in log terms, we'd be subtracting the logarithm of 0.5, but that would just be modifying the kernel of the posterior distribution by a constant. And thus, it would not affect any of the proposals or whether those proposals are accepted, or wouldn't have any effect on anything. So technically, this is wrong, but it's only wrong by a constant, and constants don't matter for the purposes of sampling from a posterior distribution. So we don't even actually go through with the truncation because that would just slow things down. Similarly, lambda has a half Cauchy distribution with scale parameter tau. Again, we don't need to truncate it because we've declared the lower bound to be 0. Exactly half the mass is going to be truncated away. So it's just going to affect the posterior kernel by a constant. And then beta has a conditional normal distribution with standard deviation lambda. I'll pass all the betas to the normal density at once in order to make this most efficient. And then, with all that said, then the likelihood is just a normal likelihood. We have some intercept, which I'm not even going to put an explicit prior on, x times beta and some error standard deviation sigma. So if we go back to the RMD file, need to pipe all this in. So I could run this by calling this Horseshoe Stan program that we just talked about. That takes like 20 minutes or so on my computer. So I'm just going to load in the object that I already created that has draws from that posterior distribution. And then we can look at its dependence. So get rid of my plot. This takes a few seconds. Here we go. In this case, we see something pretty typical, that the estimated distance correlation drops during the first part of the warm-up period, kind of levels off after that. We see it might be the case that after about 8 lags, the dependence seems to get close to 0. However, it appears that there's a bump in the road along the way. Maybe one or more of the chains got stuck, and so the dependence kind of spikes up again. Maybe comes back down. This could be an edge effect, or it could be something where another chain got stuck, etc. So this is not exactly what we're looking for in terms of some lag length at which the dependence, when draws are separated by that amount of lags, gets near 0 and stays near 0 throughout the whole post warm-up period. Another thing that's extremely concerning is that basically almost every iteration has a rug mark here on the horizontal axis, indicating there was Hamiltonian divergence for at least one of the chains on that iteration. And you will often see spikes, upward spikes in the estimated distance correlation being associated with iterations that experience Hamiltonian divergence, where the sort of leapfrogging approximation to the true Hamiltonian gets inaccurate. It exceeds its theoretical bound, etc., and thus the leapfrogging stops before it actually gets to the U-turn point, because Stan knows that the leapfrogging has become compromised. So this is not really what we want to be seeing from one of these dependence plots. Possibly it would look a little bit better if I ran out, more lags or so. But in any event, this is the mere presence of all these Hamiltonian divergences enough to make you concerned that this is not performing so well. So even the R hat statistics, which is a much weaker test or diagnostic of convergence, can be far from one for some of these parameters. So this is the R hat for tau. It's 1.25, 1.27 for sigma. These are the estimated effective sample sizes, which are so low that they're essentially meaningless. And we got a whole lot of other parameters here, many of which have R hats that are not close to one. So that is consistent with the conclusions from this, and also indicating that the chains exhibit mean differences. You might have seen me pipe in this names statement. So usually the print of a stand model, it would just be like beta 1, beta 2, beta 3, all the way up to like beta 60 something. And that can make it difficult to remember what variables the coefficients correspond to. You can actually replace the names with your own names. You have to do this pretty carefully to make sure you get the right number of replacement names, but you can do this. And so presuming that this went a little bit better, we could say this is the coefficient of body mass index on whatever diabetes symptom that we're interested in, and this was the interaction between MAP and TCH, whatever those may be. We got all the lambdas for all those as well, and then tau and sigma. But you shouldn't interpret these results because we have plenty of evidence that the sampling didn't go well. And so why is that? If we remember to our previous plot of the horseshoe prior, it was sort of very spiked at 0 and had the very long tails. And if you remember that plot, which was for the prior distribution, but the posterior distribution, if your data is not super informative, and in this case, we don't have a whole lot of data relative to estimating 65 or so coefficients and their corresponding standard deviations, that was a situation in which the curvature of the prior distribution or the curvature of the posterior distribution was changing very rapidly. And so the first derivative approximations that Stan uses in its leapfrogging approximation to the true Hamiltonian are only going to be accurate approximations for very small steps. But Stan only has one parameter that it can use to govern the step size. That's called epsilon. And, at the mode, it's going to need a really small step size, but out in the tails, it would need a really big step size in order to make non-negligible progress in and out of the tails, etc. So Stan kind of compromises by choosing a middle epsilon, and that kind of is the worst of both worlds. It's too big near the mode in order to get accurate leapfrog steps, and it's too small near the tails in order to move in and out of the tails inefficiently. And so in a situation like this, the first thing that you should do is see if you can reparameterize your model in order to make it more amenable to the NUTS algorithm without changing your beliefs about the data generating process. So again, we're going to declare the same setup, but now in the parameters block, I'm going to instead declare beta z and lambda z. And my underscore z, or anything involving z, is sort of my shorthand for indicating something is going to get a standard normal prior on lambda z and beta z. So how does this all work? And the key to this is what's in the transform parameters block, where I'm going to declare beta and lambda, which are the parameters I'm actually interested in. And I'm going to define those parameters as a transformation of the primitive parameters declared in the parameters block. So for each of the lambdas, I'm going to take lambda z, the kth element of that, pass it to the approximation to the standard normal CDF. This is a pretty good approximation for most purposes and goes a little bit faster than just using the regular phi function. So this is going to produce some number between 0 and 1, and I'm going to pass that to the inverse CDF function for the Cauchy distribution, which I actually defined up above, and we'll talk about in a second, with a scale of tau. And so if each element of lambda has a standard normal prior distribution, then the implied prior distribution, when that is run through the standard normal CDF, is going to be standard uniform. And any thing that is standard uniform when run through an inverse CDF function is going to be distributed according to the distribution whose inverse CDF you're using. And so by that, we can take lambda z, which is a priori standard normal and very amenable to nuts and stand the way it samples. It can do it with high accuracy, etc. And we're going to map that into a lambda, which implicitly has a implied prior distribution of Cauchy over the real part, positive part of the real line with scale tau. And then next, we'll use what we refer to as the mat trick in lecture, where if we have something beta z that's distributed a priori standard normal, and we scale that by a positive number, so this dot star operator indicates element-wise multiplication in stand. Each element of beta is being multiplied by the corresponding element of lambda. In any event, we saw that construction, if something is distributed a priori standard normal and it's multiplied by a positive parameter, then beta is going to be distributed normal with mean, in this case, 0, because I'm not doing any shifting of it, and standard deviation lambda. So this is another way of doing the horseshoe prior implied horseshoe prior on beta, but actually putting explicit priors on lambda z and beta z in order to make this more amenable to stand, but not changing anything about the posterior distribution from a substantive perspective. It's just now we have draws from beta z and lambda z in addition to draws of beta and lambda, and we could just ignore the draws of beta z and lambda z for the purposes of making substantive inference about this. The likelihood remains the same. Again, I'm not putting explicit priors on the intercept or sigma. They turn out to be not really needed if you have more than a few observations, or you have more observations than you have predictors. So that takes a couple of minutes to run if I were to do this explicitly. Also, I specify here that I'm only interested in keeping the draws of beta z, lambda z, tau, sigma, and intercept. And that was just to save disk space when I uploaded this thing to Courseworks. Ordinarily, you would want to preserve every parameter because it helps with the diagnostics and stuff. So that was just a disk space consideration, but you can use that mechanism in extreme situations. So if I load the previously saved object that is horseshoe prior, I can make a dependence plot for that. Takes a little while, but we see something that looks a lot better. So again, we see this precipitous decline in the dependence, after which it levels off. It's some positive amount of dependence at one lag, but after maybe not 2 or 3, because this kind of spikes up, but 4 or 5 lags out into the past, it appears as if the draws are getting essentially independent of each other. So this looks good, except for the fact that even in the post warm-up period, we still have a lot of iterations where at least one chain experienced Hamiltonian divergence, and that might suggest that Stan is still having trouble drawing from this distribution, posterior distribution. We can look out for 4 lags. This looks pretty good. If we ignore the Hamiltonian divergence, we can do the test. And I believe in this case, even though the draws are essentially independent after 4 lags, we would reject the null hypothesis that the chains all have the same distribution. In this case, the ratio of the between group distance to the within group distance at the chain stratification is 1.43, and that's large relative to the permutation distribution. And so what this collectively suggests is that the sampler is working okay, but what usually happens in situations like this is that the tails of the chains are not really that, they're similar, but they're not similar enough to fail to reject the null hypothesis that the chains have the same distribution. And so this is basically attributable to all this Hamiltonian divergence, the chains not being able to get into and out of the tails of the distribution so well. And consequently, different chains are going to have different tail thicknesses. So we can look more carefully at those Hamiltonian statistics by using the get sampler params and then doing a summary of those, stratifying by whether the iteration did or did not experience Hamiltonian divergence. And so we can see for those iterations where there was no Hamiltonian divergence, the tree depth, the number of steps that the leapfrogger takes before it hits the no U-turn point, tend to have a median and a mean of about 8, and a first quartile of 7. So that's pretty good. But in the case where it experienced Hamiltonian divergence, it's a bit less than that. So median of 7, mean of 6. So it's having difficulty taking, more leapfrog steps before the Hamiltonian approximation gets inaccurate, and it has to give up on that. We can also see over here the average acceptance probability when there's no divergence is 0.875, which is a bit higher than the target of 0.8. You can also see the case the median is about 0.96, which is way above the target, but there's a small number of draws that have or Hamiltonian situations that yield very small acceptance probabilities, and that's kind of another warning sign. Anytime you get a really skewed distribution of the acceptance probabilities, that's a sign that the Hamiltonian thing didn't work so well. And also you can see when there is divergence, the acceptance probability of the resulting proposals, which sort of by definition are not in the right place because the approximation to the true Hamiltonian has gotten inaccurate, are a lot smaller. So all of those are consistent with the idea that Stan is not quite doing the right thing for this posterior distribution, but some posterior distributions Stan currently, with its only using the first derivatives, isn't able to do, a whole lot better. Hopefully that will change over the next year when we get the option to start using the second derivatives, and then it might run a little bit slower, but it should be more reliable. We can also use the pairs function in the RSTAN package to look at the planes of the posterior distribution. The pairs function takes an optional argument condition by which you can put draws in different parts of the triangle depending on whether they satisfy that condition. So in this case, I want to use the divergence as my condition. It will put the distribution of the draws with respect to the intersection in the row in the column, that there is no divergence in the lower triangle here, and the smaller number of draws where there is Hamiltonian divergence is putting up in the top. And so what you can see in this case is there's blotches in the distribution that have a high concentration, and you can see that the like this blotch here coincides with relatively low values of tau and relatively high values of the log posterior distribution. And so this is saying that there tends to be divergence when the chain is near the mode. And, stepping away from the mode, it can't do so very accurately, has a tendency to experience Hamiltonian divergence there. So looking at these pairs plots can give you some suggestions as to how you might try to reparameterize that in order to sort of circumvent the problems that you're seeing. In this case, with this horseshoe prior, I'm not sure there's a whole lot we can really do about it right now for these data, at least. And so the horseshoe prior may be too extreme for Stan to really handle right now, at least as well as we would hope. So another alternative would be to try to use the prior on the coefficients that we talked about Tuesday, based on the implications of the LKJ distribution. And so that's given in the LKJ underscore coef dot stan function, which I can show now. So this actually doesn't even use that function. And I should have talked about that function before in the horseshoe reparameterization. So this is a function that I defined in the function block to implement the inverse CDF of the Cauchy distribution. If you look on Wikipedia, you see that it takes this form, the tangent of pi multiplied by the p minus a half. So that is going to have extreme tails and whatnot around the discontinuity of the tangent function. It's scaled up by the scale parameter, which in our case was tau, and you could shift it over by a location parameter, but we were using a location of 0. So this is an example of the function syntax you need to use when defining a function. You need to say the type of the return value and the type of each of the arguments. In this case, they're all going to be real numbers. You can't, in user-defined Stan functions, restrict these to be, have lower bounds or upper bounds or anything like that. So you just have to ensure that you're calling them with the right arguments. But these functions can be exported into the R workspace if you call the testify function on this file name, and then you can verify in R that they're working correctly. So that function I didn't actually use in the LKJ coef, and it had pretty much the same data. I'm also going to pass in a vector of the standard deviations for all the columns of X and a shape parameter for the LKJ distribution, which in this case I'm going to set to 1. And so in the transform parameters block, I declare a vector beta, which is going to be my coefficients. And it has a more complicated formula where you're basically multiplying a z vector by the inverse transpose of a Cholesky factor. Then you're multiplying that by the square root of the r squared random variable, which is constrained to be between 0 and 1. You're dividing by the z transpose z in the denominator here. So dot self is a convenience function in Stan representing the dot product of a vector with itself. So we multiply by that. That gives us unstandardized, or gives us standardized coefficients. We want the raw coefficients. So we're going to divide using element-wise division by the respective standard deviations of x and multiply by an unknown value for the standard deviation of y. So in order to do that, we have to declare all the ingredients of that in the transformed parameters block, and this corresponds exactly to the last couple slides from Tuesday in terms of the formula that we use to make the coefficients that are implied by prior beliefs about the correlation matrix between the x's and the y's. And then in the model, again, I'm going to not put explicit priors on the intercept, or there actually is no sigma, so that goes away. I'm going to use Jeffrey's prior for the standard deviation of y. This Cholesky prior on the correlation matrix among the predictors. So again, this is the distribution such that L transpose L is L times L transpose is a correlation matrix that's distributed according to the LKJ distribution with shape parameter eta plus a half. Then the R squared of the regression has a beta prior with shapes k over 2 and eta. And then the z's that go into the elliptical distribution piece for the parameters get independent standard normal priors. And then the likelihood is the same, except that the error standard deviation is going to be the standard deviation of y multiplied by the square root of the 1 minus r squared. So the error variance in standardized terms, or the error standard deviation in standardized terms, etc. So that's how that model would be implemented, and I could run all that through. Again, to save disk space, I'm not going to store the L and the Z. I'm just going to store this stuff, which normally I wouldn't do, but in order to make it small enough for me to upload it to Courseworks, that seemed necessary. Also, in this case, I'm going to change the target acceptance rate from 0.8 to something much bigger, like 0.99. That will force Stan to make smaller steps everywhere and keep it from getting dislodged from the true Hamiltonian when it's doing its leapfrog approximations. So I actually don't even need those. I can just load up the draws of that, which I had already saved. And I can do a dependence plot. In this case, I have to specify the parameters that I want included in the plot of the dependence. By default, it just does everything in the parameters block. But since I didn't save a bunch of this stuff in my parameters block, that would cause it to have an error message if I didn't put the parameters that I wanted it to consider explicitly. And here we see a very good dependence plot. Again, precipitous decline, leveling out. At one lag, there's always going to be some dependence, but shortly thereafter, maybe 4, 5, who knows, somewhere below 5, basically we get negligible dependence among draws that are separated by that number of lags. The dependence stays 0 throughout the whole post-warm-up period. We see a few divergent transitions in the warm-up period, but none thereafter, or actually only one right there. Not too much of a concern. So we can go on to look more carefully with a lag separation of 5. Again, we see a few outside the 95% confidence interval, but probably less than 5%. So we're not going to be too concerned about that. We can call the convergence test function with a thin interval of 5, and we're going to fail to reject the null hypothesis that the chains have all reached the same distribution, and then we could go on to analyze the results. So again, in this case, in order to get so few Hamiltonian divergences in the post-warm-up period, I had to specify a really high target acceptance probability greater than the default value of 0.8 in order to make Stan make smaller steps. So the last thing I want to talk about today is there's a lot of examples that come along with Stan or the RStan demo package that you can play around with on your own to see whether it's converging well or whether Stan is working well with it. To do that, you just call the Stan demo function, give it a name on one of the examples, and any additional options you want to pass to the underlying Stan function, such as 8 chains, in order to do better diagnostics. And so there's a lot of examples that originally come from bugs. And so if I wanted to call the blocker example, I could do that as follows. If I could type, so Stan demo blocker, and I think first I need to load the Stan demo. So this model, I'll show you the code for it in a second. This is just it gathering the data that it needs for that that model. It's going to take a second to compile. Good. So you can see the Stan code blocker print equal true by calling this on the model, and you can see basically how that model was parameterized. It also has a link to the original bugs parameterization of that. We could do a dependence plot for that model. Looking pretty good. Still looking good. But in this case, we would reject the null hypothesis that all the chains have the same distribution, and we might want to go back and reevaluate the parameterization of the model. These inverse gamma priors with very small shapes and inverse scales are kind of a disaster for a lot of reasons. And Stan often has difficulty sampling from models that have those priors. And so in that case, you might need to use one of the tricks that we talked about on Tuesday of taking something that has a unit scale variable and multiplying it by a scale or inverse scale parameter, or perhaps just choosing a better prior than this inverse gamma and gamma that have been popularized by bugs. If we also bring up Shiny Stan, we can take any of those examples and bring up Shiny Stan. So I would prefer this to be in the main window. Come on. Can I not have two open at the same time? Anyway, so how do I get Chinese to open? Anyway, you can't see this too well on the video, but you can certainly use Shiny Stan in order to investigate any of these models. And here are 8 examples that I could remember off the top of my head that you might want to investigate more and play around with, see if you can reparameterize to make them work better, tweak some of the settings, see if you can get them to converge reliably, and cut down on the Hamiltonian divergence, etc. So that is all for this week.